Welcome back to the Deep Dive. Today we are plunging headfirst into, I think, what is genuinely the most revolutionary technology of our lifetime, generative AI.
It really is.
I mean, this isn't just about computers sorting data anymore. It's about them creating entirely new data, new art, new music, new realities.
Which forces us to ask this huge question about creativity itself.
Yeah, can we actually build something that is in itself creative? It reminds me of that Richard Feynman quote, "What I cannot create, I do not understand."
And that quote is the perfect mission statement for this deep dive. Generative AI is our attempt to understand intelligence, to understand creation, by actually trying to replicate it.
And we're talking about machines that can do things that were, until very recently, pure science fiction.
Oh, absolutely. Painting original art, composing music that feels genuinely emotional, writing huge, coherent blocks of text, even developing winning game strategies by generating these imaginary future scenarios.
So our goal today is really to give you the map to this whole landscape.
Exactly. We're going to cover the key model families. VAEs, GANs, the diffusion models that are everywhere now, and of course, the architecture behind GPT.
So if you're short on time but really need to be well informed on this is your shortcut. We're going to get past the buzzwords and really lay out the core concepts so you understand how these models do what they do.
Not just what they output.
Exactly. So let's start with that core idea, generative AI. It feels like it's holding a mirror up to our own creativity.
It really is. It reflects not just what we have made, but the potential of what we could make. It feels like the dawn of a new kind of intelligence.
An intelligence based on imagination.
And what's so fascinating is that if you want to find the best generative model out there, you just have to look at yourself. You, the listener.
Our own brains.
Yes. Neuroscientists are sort of moving past the idea that perception is just processing input. The theory now is that your reality is actually a powerful generative model.
So I'm not just seeing the world, I'm creating it.
In a way, yeah. Your brain has been trained since you were born to produce these incredibly accurate simulations predictions, really, of your surroundings that match what's about to happen. You're constantly generating possible realities.
I love that. It makes the technology feel less alien, more familiar. But how does the silicon version do it? How does a bunch of math suddenly learn to imagine?
Well, it all comes down to the basics of deep learning. When we train a neural net, we're just trying to find the perfect set of weights for all those connections.
The weights that give the most accurate predictions.
Right. But the key question is, how does the network know when it's wrong?
And that's where the famous, almost magical idea of backpropagation comes in.
Exactly. You calculate the error, how wrong the model was, and you send that error signal backward through the network.
Layer by layer.
Layer by layer, and it adjusts all those weights just a tiny, tiny bit with every single example.
And over millions of examples, something amazing starts to happen.
Something beautiful emerges. The units in the deeper layers, they start to represent more and more sophisticated features. So for an image, the first layer might just see basic things.
Like edges and colors.
Right, low-level features. But the next layer might combine those edges into corners or curves.
And then you keep going. So those curves and corners might combine to form something like teeth, which then helps trigger a unit that recognizes a smile.
And that incredible complexity just arises from the simple mathematical goal of be less wrong. And if you could teach a model to recognize features, you can flip it around and ask it to generate from them.
Okay, let's start mapping those models. First up, the variational autoencoder, the VAE.
A VAE. It's basically a very smart compression tool, but one designed for imagination.
I like the analogy of an infinite wardrobe. You, the encoder, you place every item of clothing you can imagine onto a huge continuous map and you just record its location. The decoder can then recreate the item perfectly just from that coordinate.
Right. But the simple autoencoders had this big problem. They left huge empty gaps in the wardrobe in that latent space.
So if you picked a coordinate from an empty spot, you'd just get garbage, a distorted mess.
Exactly. And that continuity is everything for generation. You need to be able to pick a spot between a t-shirt and a dress shirt and get something new, something plausible.
So how does the VAE fix that? How does it make the wardrobe smooth?
That's the key innovation. A VAE doesn't encode a single point. It encodes a probability distribution for that point.
Okay.
And, crucially, it adds a penalty during training. It's a bit of math called KL divergence loss, and it forces all those distributions to kind of overlap and cluster together.
That sounds very technical. What does forcing the distributions actually do in simple terms?
Think of it as the math telling the wardrobe manager, hey, no empty spaces. You have to spread everything out smoothly so I can pick any random spot and still pull out a real piece of clothing. It makes the whole space explorable.
That makes so much more sense. So VAEs are great for controlled changes, like smoothly turning a neutral face into a smiling one, because it can walk through that latent space of expressions.
Exactly. Now, if VAEs solve the continuity problem, generative adversarial networks, or GANs, they introduced a totally different mechanic competition.
The adversarial dance. The generator is the artist trying to make a perfect fake, and the discriminator is the critic trying to spot it.
And they are locked in this battle, a zero-sum game, where each one makes the other better. The generator just wants to fool the critic.
Which was a revolutionary idea because you didn't need these really complex calculations of probability anymore.
You just had to be convincing.
But I've heard GANs are, well, a nightmare to train. If one gets too good too fast, the whole thing falls apart.
That's the challenge. Stability. It comes down to a lot of careful architectural choices. For example, when the generator scales up an image, it uses these special layers, conv-to-d transpose layers. And if you're not careful, they can leave these little visual bugs, these checkerboard artifacts. It's a real art, which is why models like StyleGAN and 2 were such a big deal. They finally managed to stabilize that fight.
Okay, moving on to the models that really dominate image generation today. Diffusion models.
Right. So if GANs were about competition, diffusion models are about time and gradual refinement.
The core idea seems so counterintuitive. You start with a perfect image and you just add noise to it.
A tiny bit of noise, thousands of times, until it's pure static. That's the training process, the forward process.
So the model is trained to do the reverse, to start with static and slowly, step by step, remove the noise.
Exactly. Picture a long line of TVs. The first one is just static, but each TV in the line takes the image from the one before it and makes it just a little bit clearer.
Until the last TV shows a perfect picture.
Precisely. And the amazing thing is when you start that process with brand new random noise, the final image looks like it came right out of your original training data set.
And that's why these models are behind things like DLE2 and stable diffusion. The quality and diversity are just incredible.
They really are. And we're seeing them used for more than just photos. You can train a diffusion model on a data set of flowers, say the Oxford 1-2 data set, and have it generate entirely new species of flowers.
Generative biology, basically.
Without ever touching a lab, you're just exploring the latent possibilities in the data.
Okay, let's switch from images to language. Before transformers, we had autoregressive models like LSTMs.
Right, and for them, generation was a sequence prediction problem. You have the cat sat on the guy, and the model just predicts the most likely next word.
And this is where that crucial setting comes in, the temperature parameter.
The control knob for creativity.
So if I set the temperature really low, say 0.2, what happens?
It becomes very deterministic. The model will almost always pick the word with the highest probability. So the cat sat on the mat. It's safe, predictable, but a bit boring.
But if I crank the temperature up to 1.0?
Now you're sampling from a much wider distribution. It gets more adventurous. The cat sat on the volcano or moon. The model is using its understanding of context to generate things that are surprising but still plausible.
That contextual understanding was completely changed by the transformer architecture, which, of course, powers GP2.
The key was the attention mechanism. It let the model weigh the importance of every other word when it was processing the current word. No more slow one-by-one sequential processing like in LSTMs.
But wait, if it's processing everything at once, how does it know the order of the words? How does it know the dog chases the cat is different from the cat chases the dog?
Great question. That's where you need three key ingredients. First is positional encoding. You add a special vector to each word that basically tells the model, hey, you're word number 1, you're word number 2, and so on.
So it gets the order back. What's second?
Second, and this is vital for generation, is causal masking. It's a rule that says the model isn't allowed to peek at the future. When it's generating a word, it can only see the words that came before it. No cheating.
And once you have those pieces, you can just scale everything up. From GPT to GPT-2, then 3 and 4. But a model like ChatGPT is more than just a big pre-trained model, right?
Oh, much more. It goes through this incredibly complex three-step refinement process using reinforcement learning from human feedback, or RLHF.
Okay, so step 1 is?
Supervised fine-tuning. You get human experts to write out high-quality conversations to show the model how it should behave.
Then step 2, the reward model.
Right. This is the core human part. You have the model generate multiple answers to a prompt, and human labelers rank them from best to worst. That data trains a separate model whose only job is to predict what a human would prefer.
So we're not just training on data, we're training on human preference.
It's a massive shift. You're trying to embed human values and utility right into the AI.
And the final step is the reinforcement learning part.
Exactly. You use a clever algorithm to have the main model try to maximize its score from that reward model, without drifting too far from the conversational style it learned in step 1. It's what gives ChatGPT that polished, helpful feel.
And connecting this to the workplace. These models are already changing everything, especially coding.
Yeah, through text-to-code tools. OpenAI's Codex model, which is a version of GPT fine-tuned on code, is what powers GitHub Copilot.
And the value there is so immediate. Copilot can write all the boilerplate code for you. You just write a comment like, fetch the latest tweets from this user, and it just writes the function.
It's a huge productivity boost. Programmers spend so much time searching forums for common solutions. Copilot brings the solution right into your editor. You move from searching to just refining.
Which brings us to the future, and this idea of generative AI for intelligence itself. The really big thinkers are looking beyond just training on the internet. They're looking at world models.
World models are, frankly, mind-bending. The idea is to train an AI agent to learn a task, like a car racing game, but it does it by experimenting inside its own generated dream environment.
That sounds like pure science fiction. How does that even work? How can an AI dream up an environment?
It uses 3 generative components. First, a VAE, like we talked about, to compress the visual image of the racetrack into a small, simple, latent state. We call it Ziller.
So it turns the complex image into a simple list of numbers.
Precisely. The second piece is a special recurrent neural network, an MDN-RNN. This network takes the current state Ziller and the agent's last action, and it predicts the next state and the reward. It's the AI's internal simulator.
It's the dream generator.
It's the dream generator. And the final component is the controller, a small network that looks at the state Ziller and decides what to do next. Turn left, accelerate.
And the breakthrough is that you can just replace the real game environment with the dream generator.
That's the huge leap. The controller can then train for millions of hours, getting infinite practice, entirely inside its own dream of how the world works.
That's just astonishing. So what does all of this mean for us? I feel like we're in the 4th major stage of information. First conversation, then the printing press for duplication, then the internet for retrieval.
And now generative AI for information synthesis. It's not about finding information anymore. It's about creating new insights from it.
Which immediately challenges everything, especially education. If every student has an essay writing machine in their pocket, what does that mean for homework?
The focus has to shift. It can't be about memorization and recall. It has to be about synthesizing ideas, evaluating sources, learning how to prompt the machine intelligently.
We also have to talk about the biggest weakness right now. Factual errors. Hallucinations.
Right. LLMs are just trained to predict the next plausible word. They have no connection to a ground truth or reality, so they can be confidently wrong.
Is there a path to fixing that?
A very promising one is an approach called toolformer. The idea is to give the LLM the ability to call external tools.
Like a calculator.
A calculator, a search API for Wikipedia, so when it needs a hard fact, like the height of Mount Everest, it doesn't try to guess from its training data.
It just pauses, calls the Wikipedia API, gets the number, and then puts that fact into its answer.
Exactly. It's a way to ground these models in verifiable reality.
Wow. We have covered so much ground today, from the latent spaces of VAEs and the competition of GANs to the denoising power of diffusion models and the attention in transformers. It's a lot.
And we look at the cutting-edge stuff, too, text-to-code, world models. The field is just moving at an incredible speed.
It really is.
You know, to leave you with a final thought, think about how babies learn. They spend all day playing, exploring, just building a mental model of the world, a predictive model. They're constantly generating possible futures with no real goal other than to understand.
They're building their own little world models.
Exactly. And that ambition, the core ambition of generative deep learning, to learn how to create, to forecast what might happen, it suggests that by trying to replicate this, we might be looking directly at the secret of intelligence itself. What if learning to create is the most fundamental step toward true AI?